Josh has continued. Thank you all for being here, and thanks for recording, Lucy. Josh Jones has been here for a couple of years. It's been fantastic working with him. He is quite independent, and that probably comes from his military training. He is focused on his environmental studies program with coastal issues, specifically having to do with resiliency in coastal processes. He completed his coursework while teaching fully at the Navy ROTC at the Citadel. So he would occasionally show up in his BDUs, which was a lot of fun to watch. And I never know about the yelling that may have gone on. I've never seen him yell, but it sounds like he can be a tough guy. So he's recently moved back to his hometown of Portland, Oregon. So that's where he is, a little early in the morning there. And he's accepted a job with the Department of Energy as a hydropower production coordinator. Today, Josh is going to give us his presentation. He's going to take about maybe 25 to 45 minutes, depending on how long he has put together and how quickly he speaks. Then we'll take questions from the public. Once those are done, we will then meet with Josh, just the committee, and have discussion with him, ask questions, clarify anything that we have not clarified since we've looked at his thesis drafts, and have that deliberation. Then we'll bring Josh back in the meeting and have those discussions. And then I guess right now, Josh, the floor is yours, and you have screen sharing capability. So please go on, and if I can help, please do not hesitate to ask.
All right. Thank you very much for that intro. I'm just going to go back to the beginning. Click. And can everybody see the PowerPoint fully?
Yes.
Okay.
Yes.
All right. So thanks for the intro. My project is called Using 3D Imaging to Evaluate Physical Processes on Living Shorelines. So I'll get into how I did that, the methodology created, the results, and some future work that can build upon this methodology. I'd like to, first of all, thank my committee members, Dr. Scott Harris, Ben Stone, Dr. NK, Caitlyn Meyer. I appreciate all the guidance you guys have given me, especially on this project that is kind of independent and has to be, the methodology had to be created. And also I'd like to give a big thanks to Berhone Tomiso, who worked at the High Performance Computer Lab, and Dr. Alves Benitizo. I'll get into his help a little bit later on, but it's been great having so much support for this project. So before I really get into anything, I'd like to cover what is a living shoreline before we even start talking about it at all. So NOAA has produced a definition that's generally agreed upon. The living shoreline maintains continuity of the natural land-water interface and reduces erosion while providing habitat value and enhancing coastal resilience. And it can be done multiple different ways: oyster reefs, marsh grasses, coral logs made of coconut or other natural fibrous material. There are many ways of doing it. It essentially works to block, redirect, or absorb the wave action so that sediment can build up on the landward side, like in the picture shown there, protects vegetation upwind. It produces habitat, which initially was kind of the push for these living shorelines. South Carolina has reduced their oyster population over the past 100, 150 years, and especially oyster reefs, clean water, produce food and shelter for other living creatures. And it enhances resilience. There are some recent studies that show that these living shorelines, unlike flat concrete or steel seawalls, they actually grow over time, and in some cases can increase their height with sea level rise. And they also absorb wave energy instead of just necessarily redirecting it to other places like a lot of seawalls have. That's why a lot of times on the end of seawalls or jetties, there are spots that are eroding extremely poorly, even though the seawall protects what's directly behind it. So that is what a living shoreline is. And recently, living shorelines have become a lot more popular, especially in South Carolina. The DNR's SCORE program has been for years and years collecting oyster reefs from the public at different boat docks and from restaurants who recycle their oysters. They give their shells to DNR, they pick them up, clean them, prepare them, set them up in a few different ways. A very common way is to put them in bags, place them strategically along the coastline. DNR also builds some other things like concreted crab traps, where they get crab traps that are either left over or found, dip them in concrete, and that provides a really good surface for these oysters to build on. Oysters really love building on old oyster shell, but other hard surfaces work pretty well too. So that's living shorelines, and this project is really focused on living shorelines built from oyster reefs. There are a lot of them in South Carolina, and that is a big part of the DNR program. Now, unfortunately, there have been very few studies on living shorelines. Part of that is because they're a lot newer. We've had seawalls for decades, centuries in some cases, and we've been able to put them on wave labs starting in the 20s and get years and years of very quantifiable data on them. It's not really the case on living shorelines. It's a little bit tougher. Part of it just comes from their nature. It's pretty hard to pick up a living shoreline and move it someplace where you have the equipment. So what a lot of studies have done is look at GPS data, look at imaging, and try to see how much it builds up or erodes over certain years. There was one study recently in Alabama that showed that living shorelines made of oyster reefs reduced erosion by 40% over 2 years. And then another study in North Carolina found that they actually changed some spots from losing sediment, accreting, to actually building up sediment. So it's a pretty nice change. But if we're looking at this really for protecting properties, especially on private property, doing things that are more short term, it would be really nice to look at individual waves so that we can compare them to seawalls, dikes, things like that. And like I said, it's pretty hard to get these things in a wave lab. I've really only found 2 studies where they did quantifiable data on individual waves. One of them is the picture there, where they made it and they actually got it into a wave lab, and the scientists doing this put out one with just oyster reef, one with just marsh grass, and one with them combined, and looked in the difference over a couple of years. Came up with some good data that basically showed the more living shorelines you have, the more it will reduce wave height and energy. However, that's one of very few studies, and it would be nice to get more studies from different sources on that for things like permitting and state regulations. So the goal of this project is to get quantifiably measure living shoreline impacts on individual waves and come up with a methodology that can be deployed where these living shorelines are along the coastline so you don't have to move them. They can be repeatable, so you can do it off of one area and then go to another coast where maybe the waves are a little bit different and see how that works. Mobile, because really you want to be able to take this from spot to spot, and low cost so that it can be deployed easily, repeated, so that other people can get similar equipment at a relatively low cost and continue the study. So these were the original hypotheses proposed. In a sec, I'll go to some modified hypotheses. And this is based off of the couple of studies that have existed for living shorelines. So the first one is a wave that interacts with a living shoreline will have a significantly lower mean height versus a site that's a control, a site without a living shoreline. Second one is very similar. A place with a living shoreline will have significantly lower wave energy. Energy and height generally go hand in hand. The third one is that as the living shoreline increases in height off the pre-installation level, it will have a greater effect on the reduction of both wave height and energy. So that's basically, it makes sense. As these things grow, as the oysters build up over time, we would expect it to have a bigger difference, and it would be great to quantify that difference so that we know, hey, if you install a living shoreline, we expect it to go this much in the next few years, and then by year 4, 5, 6, have this much protection for your property. And then finally, the difference in wave height depends on the construction technique used to restore the oyster reef. For example, mesh bags with oyster shells may be more effective than concreted crab traps. That's something that really hasn't been evaluated. I know DNR is working on a long-term study looking at all that, but in terms of individual waves, that's something that hasn't really been evaluated before. However, due to some technical issues, some processing issues that I'll get into, I had to modify the hypotheses. So the first one is a video segment that shows a series of waves after interacting with a living shoreline will have a lower number of matches per frame versus a control. And I'm going to get into what that term matches per frame really means in the 3D imaging analysis. And then a video segment with a lower Beaufort scale will have a lower number of matches per frame. And again, I'll talk about the Beaufort scale and how it applies to this project again. So this is the study area. I chose Fort Johnson for a few reasons. One, it's very easy to get to. So I could go multiple times. I could look at the weather in the morning, see, oh, it'll be good for tides weather, and zip over there. So it's a really great place for opportunity. And DNR has built a lot of different living shorelines and a lot of construction methods over a lot of years. So this is kind of like their petri dish for living shorelines there. So it's a great place where you can look at different construction methods, different ages, and things like that. And you can see in the image on the right, the zoomed up image, the gray areas just off of the shore are some of the living shorelines that could be evaluated. So there's a lot to look at there in a very convenient location. All right, so now I'm gonna get into some background on 3D imaging. This is the methodology I use and built off of to look at these living shorelines. 3D imaging essentially boils down to you have multiple cameras, at least 2, looking down at from a different place and slightly different angles in some cases, looking down on the same area. And then you take those 2 images that are lined up at the same time. Excuse me. You take those 2 images, they're lined up at the exact same time, and you basically do trigonometry, or rather a computer does the trigonometry, finds where the images match, and then looks at the peaks and troughs based on different areas. This has been used in a couple previous studies we've had in the past. A lot of them are deployed on ships or off of piers. So there's been quite a bit of study using 3D imaging for wave analysis that I use to modify here. And then for this project, part of it was making it low cost. And with the help of Dr. Harris and Lucy Davis, we got some great Raspberry Pi cameras. You can see the image there with the rubber bands to make sure it doesn't fall off at all when I'm moving it. But they're very small cameras. It's about 3 inches by 1.5 inches. They're about $105 all included. And they have, for their size and price, they have actually really good qualities for sensor resolution. And they're very adjustable. Lightweight, so I can mount them easily, move them easily rather than a big clunky camera. And each camera has its own Wi-Fi connectivity. So I was able to deploy them throughout the day and then just have my laptop out and monitor, make sure each camera was working properly, was downloading, was recording, was syncing up as much as it could. So it's a really good piece of technology that could be used throughout the future. And then to get a good picture of the images, I built these camera stands. And like I said, we wanted this project to be mobile. So what you see is the camera stand disassembled in the back of my car that I would drive out to Fort Johnson, and it could easily fit in a small car. And then you see one built up waiting for the incoming tide on the other side. So it basically collapses down and then uses a couple tripods on each side and then one stabilizing pole at the back. The first few times it didn't use a stabilizing pole, and it had too much bounce from the wave and the winds, so that the images weren't very useful. And then what you see on the board there are two Raspberry Pi cameras with their battery packs. And these stands were built to be adjustable, so I could change the spacing between the two cameras to try to optimize that. And this is a couple images of my field setup. So each stand has a pair of cameras like you saw previously. And you can see in the lower image, the camera stand on the right is just behind a living shoreline, kind of an older oyster reef there. And just to the other side is a control site that DNR left just to look at for their own experiments. So this is a great spot where you can have 4 cameras total, 2 stands, looking at the same time at a place with an oyster reef and a place about 10 feet away without an oyster reef. You can look at them at the same time and look at really the same waves interacting through them. Okay, so now I'm going to get more into the methodology and the prep work that goes into this. A bit of it will be coding because these Raspberry Pis require you to build your own codes in them. They're very versatile, but it takes a little bit to get into making them as useful as you can be. So to start with, I got into this program called crontab, where it basically said at 0600 on this date, start a video or execute whatever command follows. So it's really nice having a preset start time so that the morning of or the day before I would go out to Fort Johnson, I would set up all these cameras with predetermined start times, doing minute-long or 5-minute-long videos. And so that I would open up my laptop and just be able to monitor them rather than having to go in multiple times and say, start a video now, end now, that kind of thing. And then I had to write a couple different codes. This first code was the kind of default code for making videos on the Raspberry Pi camera. I'll go into a little bit of detail there. The first part, Raspy vid, it just means orders the camera to take a video. The -T 60,000 means take a video that is 60,000 milliseconds, which works out to be 1 minute. That's kind of the default go-to there. And then the -O followed by 2020 05 03 12 02. That was basically the code to be like year 2020, the 5th month, which is May, on the 3rd day of that month at 12 o'clock. And then the A means this is camera A. So that was my own way. So that when I combined all these videos later, I knew that it came from what I called camera A. And that helped a lot with calibration. The H.264 is the video type for it. It's called H.264. And then the -CFX 128 means take a black and white image. For the computer program I did, the images have to be in black and white. And then the -FPS 50 means do it at 50 frames per second. This is a great thing about the Raspberry Pi cameras is that you can tell it to do as many frames per second as you want, and it will do. It's very adjustable. However, with this code, I found there were a few issues. It wasn't really designed for exact time for scientific things. So it got a little bit of frame skipping, which I'll talk about more in the results section. So I eventually had to adjust the code to a little bit more robust one. That's the bottom code here. Again, it says Raspy vid. So take a video. I had to put it in what's called mode 7, and that allows for higher frame rates. I then also had to adjust the pixel. So the -W640 is a width, of 640 pixels, and minus H 480 is a height of 480 pixels. The minus FPS is again frames per second, and I was able to go up to 80. I found that higher frames per second really helped on these smaller waves. And again, it was a 60-second video with a similar naming convention and black and white. Those were the two codes I use, and I'll get into the results on how they differ. And also, before I really got to analyzing any of these videos I took, I had to get all the cameras calibrated. Essentially cameras, you can even see it on your own cameras. They have lenses that do some curvature. And if you ever watch old Western movies, they put in cameras with those large curvature lenses to really capture things. It's good for cinema, but not really good for scientific evaluation. So we had to go into MATLAB. There are programs that essentially flatten that curve using something of a known dimension. So in this case, use this chessboard pattern. MATLAB then saw, hey, these things should be perfect squares. So this is the math to uncurve that camera. And that goes into the program used for analyzing these. The images also have to be in a special numbering order. I won't necessarily get into the details, but the analysis program I use is very strict on the numbering order and the naming convention. And then finally, the images have to be in what's called a tagged image file format, TIFF. So I had to use another program to extract the images from the video, get it so that instead of one document, one file that's a 60-second video, it would then be 60 seconds times 50 frames per second or so, and come up with then that many images. And that finally leads me to this program called the Wave Acquisition and Stereo System. It was developed by the Italian Institute of Marine Science just for this, for analyzing wave data using 3D imaging. And I really would like to thank Dr. Benetazzo for creating this and for corresponding with me on some technical assistance throughout the project. It's done a very good job of accurately measuring wave height. In one case, it got to within 2.3 centimeters, which is well within what you need for pretty much any project. It's been used all around the world. I think it's been about 8 or 10 published studies now. They typically use very expensive cameras that are about $500 to $1,000 each, which wouldn't really work for this project when you're trying to do multiple cameras at the same time and deploy them in a place and get them so that you're trying to move them. Those big clunky cameras wouldn't be very good for this. It also requires a very, very large computer to process these images. If you're thinking about it, processing 1 minute of video at 50 frames per second, that's already a lot of images. And then it has to look at every pixel and then try to find a match and do a 3D performance for that. And that's where I really would like to thank the high performance computing lab here that made that whole process so much easier to have their large computing power. So this was the program I used. 1 second. You can see on the previous screen, there's a few different steps that we'll talk about. The first step is just prepare, where it counts the number of images, creates an output file. And this pair of images is from the test data. When we downloaded WASP on the HPC, we were able to run the test to make sure that it worked properly. So you can see those are 2 images, and you can even tell the waves are a little bit offset the way that they should be. The next process is match, where it looks for distinguishable pixels and the pixels that surround them. And it basically lines them up so that the user can see those yellow lines are one pixel on one image matching another pixel on another image. It then goes through this process that filters out those matches into what's called inliers. Try to get rid of some that are from glare or shadows and those kind of things. And then I will even show a short video here on kind of what the output is. One second while the video loads. So what really this should end up looking like is at the end, an image. Can everybody see the image that's on the web page? Okay, so it should look like this. Now this is overlaid with an actual image from the area, but you can see the elevation changes, red being the highest, the peaks, blue being the troughs. So basically takes an image, looks at those different spots, and then does its 3D processing. And then you're able, if you want to, overlay it to get a better visual on it. It also comes up with a 3D data set that can be used for other methods of processing. So I'll get back to this. Okay, so that was a part of the WASH program that I utilized, was really the prepare and the match step. And then for the other parts of the hypotheses, the modified hypotheses, I also looked at the Beaufort Scale. This has been used since the 1800s to look at wind going across the ocean. In this case, the waves were basically wind-produced waves. So that kind of makes sense to use this. And it's a good way to kind of visually quantify what the waves are looking like. So I did this for each video segment. And then the goal is to really consolidate the data. So what I decided I could do is label each image or each segment of video, date, time, what cameras it was using, whether a living shoreline was present or absent, its number according to the Beaufort Scale, and then looking at the total frames in that video segment. Some videos were longer than others, so it kind of varied. And then looking at the total matches. And then really the important things are the matches per frame, those matches on the match step of WAS, and then the inliers. So after filtering out some of the extra matches from glare and shadows, really what does the image come up looking like? And then looked at the statistical analysis of those matches versus the presence or absence of the living shoreline and versus the Beaufort Scale to try to get some method of looking at that. And for the first part, I used a two-sample t-test, and for the second hypothesis, I used the ANOVA test. Both were in R. And these are kind of the initial results and kind of the issues I ran into for the first 4 initial hypotheses. It turns out getting these Raspberry Pi cameras to synchronize took a little longer than I had hoped. The original code, like I said, had some frame skipping. So I would go from one frame and then the next frame might be a couple milliseconds later, which for most purposes isn't a big deal. But when you're trying to line up one camera to the other, any frame skippage of just 1 millisecond could, 1/50th of a second or something, could be a big deal. And then unfortunately they had some slightly offset start times, even though these cameras were both, or all the cameras were hooked up to Wi-Fi. Their internal mechanisms could be off by a 50th of a second or something like that. So I had to go through and try to manually correct for the start times, looking at waves, looking at features, and then reset the numbering convention so that the final images would line up. You can kind of see the difference of these two images. They definitely look like the same wave, but when you're talking on the scale of 50 frames per second, getting slightly off can be kind of a big deal for this. And then the other big issue that I worked with and that Dr. Benetazzo kind of said was one of the big issues here is having pretty few discernible features. If you look, all of these yellow matches from my own data on one of my field days, they're really focused on that wave crest, which is kind of inherent to doing this close to the shoreline instead of spread out over the entire image. They're focused on the things with distinguishable features, the things that aren't really just flat. And then I came up with an average of about 12 per pair, unfortunately, whereas previous studies had 500 per pair. And then when I tried to filter, that was after filtering it out, to come up with about 12 per pair. That really prevented any further analysis in the WASP program. It would try, but it would just come back as we don't have enough matches to do a 3D analysis of this. You really need things on the scale of hundreds of matches per an image. And this just wasn't cutting it because of, like I said, the timing issues, the fact that it was really focusing on wave crests and things like that. And this was one of the big reasons why I changed the initial hypothesis to, instead of looking at the actual 3D analysis from the WASP program, to instead really looking at the number of matches per frame. Because at least the number of matches per frame can give you an idea of the roughness of the surface. And based on what I would see out there just visually, I could kind of tell that, well, the living shorelines, the places with a living shoreline look a little bit less rough. There's less big wave crests coming through them. So even though this isn't a perfect 3D, this is the exact wave height kind of thing, it gives us a pretty good idea of the roughness and the general wave activity. Like I said, glare became quite an issue. You can see the difference in, cloudy, less intense glare. The glare is still there, but at least it's spread out a little bit more. And then on sunny, if I had a sunny day with sea foam and a bright glare, it was kind of rough for that. I initially looked at using a canopy, but it's hard to cover the entire area in a canopy. And it's kind of hard to find a cloudy but not rainy day in Charleston. So what I did was consolidate the data for my modified hypothesis, like I showed earlier. This table is just a little fragment of the actual table. You can see the date, different days I went out there, such as December of 2019, the time, camera pairs, P for presence of living shoreline, A for absence, and then the Beaufort Scale analysis, total frames, matches, and all that. So I consolidated this whole data and then got it through the R program to do the statistical analysis. This is what we came up with for hypothesis number 1, which is a video segment that shows a series of waves after interacting with the living shoreline. We'll have a lower number of matches versus the control where the wave is unimpeded. Really didn't get any strong evidence of that. There were a couple days where I got values that are between 0.05 and 0.10, which in statistics is considered some moderate evidence, but not really strong evidence of a correlation. It basically shows that in a couple of cases, this is shown to be true, but can't really say that it's definitive in any way. And then the results for the second hypothesis were pretty similar. This one shows that video with a lower Beaufort scale will have a lower number of matches per frame. Again, it's trying to just figure out, is this methodology working when I compare it to what I see visually? And it came up again with a couple cases, had some moderate evidence. So more research would be good, but we can't definitively say that there is a correlation on the whole. So this is kind of the discussion going off of those results. The Beaufort scale has some issues. basically most segments were rated as either 1 or 2. There's no 1.5 on the Beaufort scale. So it's very discrete like that. It's hard to distinguish more precisely. Like I said, image synchronization could be improved. Specially designed cameras, they're bigger, they're clunkier, they're more expensive. They're also more expensive because they are designed to do everything synchronized and stuff like that. And looking at these close-in waves close to shore makes it a little bit tougher. We saw that small waves that are cresting usually have one per an image, which really focus the matches in one small area, which isn't ideal for 3D matching. And they produce a lot more glare when they're cresting like that. So in conclusion, we saw that there's some statistical correlation, but not necessarily anything proving it, any strong statistical evidence. The methodology could use some improvements. This was a building my own methodology type project as we went through. So it definitely got better over time, but given infinite time and resources, it could be improved by a lot. And these things are important because living shorelines are gaining attention. SCDNR, I think, just wrapped up one of their big long-term multidisciplinary studies about living shorelines. And the Department of Health and Environmental Control is evaluating permitting for this. And it would be great to have more data so that the permitting process could have more weight behind it and basically have more quantifiable things so that we can implement this a little bit better. Okay, so that is my presentation. I'll now open it to questions.
Yay. There's a lot of clapping going on, really. You can hear it. If you'll go ahead and unshare your screen so we can see everybody a little closer, put you in the center stage here. Can you unshare your screen?
Oh,
down the bottom, just the green. There you go. That's better. Excellent. We might need to come back to some slides, but so at this point, we will take questions from Will, if Will has any questions, or Lucy. Go ahead, Lucy.
I have a question, but I did take a coffee break in the middle of this, so I may have missed it. But can you tell, and I know it would be hard, but can you tell like what is causing the wave action?
So on these days, it was wind. Basically all the days I was looking at was wind. I was trying to expand this to look at boat produced waves because that is a big issue, especially on some very specific sites in South Carolina. But when I started looking at the methodology, I decided to really focus in on Fort Johnson and work more towards the methodology. Didn't really have the time or ability to expand that to boat produced waves.
Okay, that sort of led into my next question. So you may not know the answer, but based on sort of your data collection, you may be able to generalize. How do you think that your data collection and your results would differ based on your analysis at Fort Johnson along the harbor versus if you did it along Shim Creek, which has a little bit more of recreational activity, more boat activity, I would say maybe less policed activities. I've seen people like walking around in the marsh over there, definitely putting their kayaks and all that sort of thing. So what are your projections on how that would differ?
I think that it would improve it, basically because the bigger the waves are, the easier it is to tell differences between them. So the easier these waves are, usually the easier it is for cameras to pick them up. However, if I were to look at bigger waves, boat produced waves, I would probably have to increase the height of those stands a little bit just to get a wider angle. But I think on the whole, if I were to continue this project, that would be my next thing is scaling up a little bit and looking at boat produced waves, because I think it would make it easier to pick up those features.
Okay, thanks.
Yeah, I just have one question, and it's a technical question related to those cameras, which I'd never heard of before. What's their lifespan in the field, either battery life between recharges or just durability?
Oh, that's a good question. So they don't actually come with their own batteries. These things are, I guess the best word to use is like as adaptable cameras as you could possibly imagine. So I ordered my own batteries, and there's a micro USB connection between them. The batteries I use while they're recording video and everything probably lasted about 3 or 4 hours. Now there are people who take these Raspberry Pi cameras and they have huge batteries, or they plug them into the walls and have infinite power. But if you got bigger batteries, which are easily available, you can make them last all day. And your other question was the camera's durability.
Yeah, yes.
So it is plastic. So you don't want to throw them anywhere, but I kind of modified the case a little bit. They have different cases you could use. I'm sure metal waterproof cases are available online that are just more expensive. Oh yeah, Dr. Harris has one up
So
there.
this is one that's in a plastic case, Will, and
Right.
obviously not good for the elements. If I don't mess up here, I won't be able to get that one over there, but you can put them in waterproof cases. I've had several deployed out in the field for several years that are hooked up to 120 power, but you can put them on solar as well with batteries.
Cool. I look forward to reading through your thesis when it's available for public use to learn more about this.
All right, yeah, there are some really nice cameras, and actually midway through the project, the Raspberry Pi Foundation came up with their high definition camera, which I was like, oh dang, I wish I had, wish this had come out 6 months earlier, because that looks really nice.
Cool. Thank you.
Yes, Lucy.
I have one more question. You mentioned permits a little bit on your final slide. Can you expand a little bit on how these results will impact permitting and policy?
So basically, the state of South Carolina and a lot of states are very used to seawalls for protecting coastal areas. And they've built their permitting system around the use of seawalls. So I'm sure Ben Stone knows a million times more than I do about this, but it only takes a few months to get a permit for a seawall on private property, because it's really known, these things have been in wave labs since the 20s. So it's known that this height of wave for this height of seawall, we're expecting it to fail only at, so many wave events over so long, or to crest it at this. But we really don't know what happens to those individual waves as they're passing over a living shoreline. So if we were to know that, then it would make the permitting a little easier. That, hey, if you want to protect a building that's 20 feet away, you really should have this much width or length of a living shoreline and put it in with this dense of oyster reefs, and that will absorb enough energy over the period so that it doesn't get to your house or stuff like that. And my understanding is that still the permitting process for this in South Carolina takes about, 3-4 times as long, because it's, instead of like a standard permit, it's basically a write your own permit type deal.
Okay, that makes sense. Cool, thank you.
Any other questions from the audience? And we're going to go to the committee here in just a moment, if that's okay. Now, Lucy, does the committee usually do it by ourselves? Do we kick the audience